This lab investigates gravitational motion using computational modeling. The goal of part one was to determine the mass of an unknown black hole by analyzing the motion of a star orbiting around it. In part two, we simulated a spaceship orbiting both a planet and its moon by calculating gravitational forces and predicting the motion of the system. In part one, the system was the star that was orbiting, and the surroundings was the black hole. In part two, the system was the spaceship, and the surroundings was the planet and the moon. Just an overview of the results was for the first part of the lab, the black hole estimated mass was approximately 4.4 times 10 to the 94 kilograms, and an initial spaceship velocity of -10, 1350, and 0 meters per second led to a stable orbit that didn't crash. The main physical principles we used in this lab was the Newton's law of gravitation and Newton's second law. Newton's law of gravitation says that the force of gravity is equal to -g times both masses over the distance between them, r to the power of 2. Newton's second law, F equals ma, was also interpreted to be equal to F net equals dp over dt, which is the derivative of momentum over time. We also use the position and velocity updates that we used in previous labs as well to update the position and the velocity over time. For curving motion, we split the total force into parallel and perpendicular components. F net parallel was responsible for speeding up and slowing down, which was the equation we used was P final minus P initial over delta T. And for perpendicular total force, it changed the direction, faces inside the orbit, and we used the equation F net minus F net parallel. For the first part of the lab, the initial velocity was derived from our Georgia Tech email. The star mass was 2 times 10 to the 30 kilograms, and delta T was equivalent to 1 Earth day in seconds. We used the momentum update by first calculating V initial and V final, and then taking those and multiplying it by the star mass. Since net force was split into perpendicular and parallel directions, the parallel was found using the magnitude of the delta P over delta T times P hat, which was the unit vector of the initial momentum, to get the force responsible for the object speeding up or slowing down. For perpendicular, it was calculated using vector subtraction, ending up leading to the turning and centripetal force, which was just the total force minus the parallel force. We rearranged the gravitational equation to end up solving for the black hole mass, m2. So multiple mass estimates were then calculated and averaged to determine the final black hole mass. The average was calculated in Google Sheets to equal 4.41 times 10 to the 94. Blue in this represents F net. Orange represents F net perpendicular, which faces the inside of the orbit. F net parallel faces the direction of motion. For part two, we simulated the motion of a spaceship traveling near a planet and its moon. The goal was to find an initial velocity that allowed the spaceship to orbit both bodies without crashing into either one. In the orbit to the right, as you can see, they don't crash at any point in the system. The initial spaceship velocity for this curve was -20, 1320, 0 meters per second, and the Tmax 2350, which is the moon's orbit. We made sure to understand that the gravitational forces were acting on the moon from the planet and spaceship, and then the spaceship was experiencing forces from both the planet and the moon. So using all these forces, we found what R was. We then calculated what the force was using universal gravitational equation, and then we updated the position and velocity using Newton's second law. We were able to create a trajectory where the motion of the spaceship was influenced by both gravitational sources and didn't end up leading to a crash. When we're thinking about net force and its perpendicular and parallel components compared to rate of change of momentum's parallel and perpendicular components, they are technically equal to each other. This is exact with perfect physics. However, in our lab, we don't get the chance to measure force directly because it is impossible with the objects that we're working with. However, we can estimate it through the motion that we see. For the rate of change of momentum, we separate the motion into its parallel and perpendicular components to help estimate what net force is. However, we would typically take what the net force is and then split it up into its parallel and perpendicular components, which will just be forces in the different coordinate directions. X, Y, and Z are examples of that. If all of the objects between both labs were included into a single system, there would be various different interactions between each and every single object. In this case, some interactions will be the most dominant. The largest mass especially and the smallest r will be the most dominant interactions based off of the way that the equation is set up. The largest mass in this case is equal to the black hole, which would be the strongest interaction. Some sources of error could be found in approximating the net force with the change in momentum over time, especially over large time steps, which which in this case we were doing one Earth day, which could lead to some errors. And also for the mass prediction, we average the values of the estimates, which is never fully accurate. Thank you.